Good morning. This is ChE2176, and the course is about learning how computers work and how we can use them to simulate and control chemical process operations. My name is Kumar. I go by the nickname Kumar, and I apologize at the outset for not being in the lecture live. This is a pre-recorded lecture, and I've asked my postdoctoral fellow, Dr. Lec02, to be present to run this pre-recorded lecture and pause it at times when you have questions so that you can answer them. The recorded lecture is also available on Moodle so that you can listen to it on demand anytime you want from a variety of sources. I will record every lecture during this course, but sometimes when I am traveling, I will pre-record the lecture and put it on Moodle. And then I will have somebody in the class to play it for you and then respond to your questions and answers. There are a few other experimental things that I'm doing this term. One is called a program called Acadly. And I think many of you have already received invitations to register in that. And that will be used for online forum discussions, Q&As, and also for taking attendance during the lecture hours. You are required to attend 2 lectures per week, Monday and Wednesday from 10:30 to 11:50. And one of the 2 labs, the labs are either on Wednesday or Thursday. It is from 1:30 to about 4:20. I will tell you a little bit about the structure of the lab shortly. But before I do that, I want to pause at this stage and ask Jilin to take attendance, which essentially means that he will log into Acadly at this stage, and then you'll be able to register your presence here. And it shouldn't take more than a minute, but this is the first time we are trying, so there may be some technical hiccups, but let's see how this goes. So Jillian can pause and then resume that after the attendance has been taken. Okay, assuming that the attendance has been taken, let's continue. So let me open up the Moodle page for this course, and that is the page through which I will distribute all the course material, and all of you should have access to it. And the front page of the Moodle web page will look something like this. So there's some description about the course, and then the materials that you can download, for example, the course outline. And then there is a formula sheet that you will be able to download and bring it to the exam. And then there are additional material that I will put on MATLAB and other resources for people that learn additional material to learn. In addition, I have put links to the previous versions of the recording for this course. Not every lecture is identical, although the contents that are covered in general are the same, because the interaction in the class can be different. So you might find it useful to listen to other versions of my lectures from the past years on YouTube, and you will find, for example, the links to them week by week for lecture by lecture. So for the first lecture, today's lecture, there are some older versions of these same lecture, and there may be some differences in quality of audio recording, etc. I hope you can bear with that. So there is a MATLAB student edition of the MATLAB that's available for about $99. I think you can order it online if you like, and download the software and install it on your own PC or Mac if you so choose. In addition, you will have MATLAB available in our chemical engineering labs, and also in a number of labs around the PFT building, and perhaps in the library as well. In addition, you'll be able to access MATLAB and other software like HYSYS that we are going to use via BLab. This is the virtual lab. So from home, for example, even if you don't have MATLAB on your computer installed, you'll be able to follow a procedure to log in to the university computers and access MATLAB in a virtual environment. From a functional point of view, these all would be identical once you start running the MATLAB software. Okay, so in addition, sometimes I might have a kind of a virtual help session, typically on weekends, for those that need help in doing assignments. So this will be achieved through using web seminar-like environments, and there is a link to the virtual classroom in the Moodle page, and I will announce the date and time, and you'll be able to click on this link and reach out to that classroom. Typically, we have half a dozen students showing up and asking for help on doing a particular assignment or during preparing for the midterm exams. So Moodle will be the primary source for distributing the information, but Academy is another source that we will use, as I said earlier. This is a new web-based software that is free for the first year at least. So let's see how that looks. Once you log in, you should be able to see this particular course web page, computational methods. I'm not sure how it looks from a user point of view, but this is what I create, the contents, again, lecture by lecture. I will distribute material, etc. And we will take attendance as well. Attendance will become automatically active, I believe, during the time of the class when the instructor logs into this website. So there are kind of similar functions for both Moodle and Academy, but Academy has some nice interactive feature for messaging each other and sharing answers to questions, etc. Okay, so we'll experiment with it and see how that goes. Let me open up the course content, the outline. You can click on it and download it, but I will open my version from my laptop and take you through some of the requirements for the course. So this is the fall 2018 version of this. Okay. So here you have my contact details, and as I said, I go by the nickname Kumar, and this is my email address. And so the class schedule, Monday and Wednesday, 10:30 to 11:50, and the lab is either Wednesday or Thursday, 1:30 to 4:20. The labs will be in PFT 1124A and B. These are the computer labs for chemical engineering, and the lectures will be in PFT 1225. You already know all these things because you are here. The course outline essentially lays out what are the prerequisites and what are the course outlines. And my office is in 3314H, and I have scheduled office hours on Mondays from 8 to 11, but I will be available anytime for you to drop in. As long as I have no other scheduled meeting, you can drop in my office. So it's kind of an open door policy. And in addition, you can email me and fix up a particular time if this time is not convenient, the scheduled office hours is not convenient for you. I will try to help you as much as I can. The textbook, which should be available in the bookstore, is Computational Methods for Process Engineers. We wrote this some time back, and I'll be taking a lot of numerical methods material from there. For MATLAB material, I will distribute additional material. Now, for the assessment rules, assignments, there will be about 8 or 9 assignments, and they will be worth about 20%. There will be 2 midterm exams, each worth about 20%. And I have already put the date. The first one is on September 17th, the second one is on October 22nd, and the final exam is scheduled by the university for December 7th, and that will be worth 40%, so making up a total of 100%. The assignments will typically be distributed through Moodle, and you will submit by Moodle. So you will submit an electronic file, either in the form of a PDF file or a Word file, and I will tell you how to generate these files as a response to the assigned problems. I will not accept any in-person handed sheets that you hand to me. It has to be submitted to Moodle on time. Moodle will shut off the submission at the prescribed time. So on the due date, it will shut off by 4 p.m. If you delay even by 5 minutes, it will not accept it. And please don't email me saying that some excuse for that. So you need to plan your submission deadline so that you submit it by the deadline. And this is the way that the real world operates. So you need to get training to that kind of a discipline. Okay, so again, I emphasize submission by any other means will not be accepted. Okay, as I already said, communications and feedback, it's mostly through Moodle and Academy. Academy is a new experiment, and the recorded lectures are all available from past years in this YouTube space, but the current recorded lecture will be available only to the registered students in this course through Moodle, and later on I might upload it to YouTube to make it available to the general population. Now, the learning outcomes are listed here. I'm not going to go through each one of them in detail, but I will tell you the general outline of the course shortly. Now, the general rules: do not use cell phones in the class. Please turn them off. You may want to use it during the attendance time, either from a laptop or a cell phone or a tablet. But outside of that, I don't want you to be browsing around with internet. Do not, of course, engage in any disruptive behavior in the class. The rules about late assignments: you will get a 0. There is no overruling. Okay, and late assignments will not be accepted or marked by the TA. Class participation is strongly encouraged. During the lab hours, on several occasions, we will have a quiz, maybe 30 minutes, cutting down to 15 minutes as your MATLAB skills become better. I would like 3 of you, up to 3 people, can work together as a group in doing the quiz. The quiz typically will be given at the end of the lab session. And once we have finished all the lab work, we will begin the quiz session. And at the end of the quiz period, I or the TA that is present in the lab will reveal the solutions to the quiz. And what you will do is you will exchange your quiz sheet with your neighbor, and then you will grade the sheet that you have received from your neighbor, and then hand it back to the TA or me for recording. Your class status will be posted on the Moodle with the quiz marks, assigned marks, etc. So you know where you are in the class. In the quiz, all members of a group will get the same grade, the same marks that the quiz deserves. Okay, plagiarism will not be tolerated. That is, those that submit copied work, copied programs, etc., will get 0 in that assignment. And I'm not going to be arguing who copied from whom. If 2 assignments that are submitted are identical, both assignments will get 0. Okay, that's first time, and if it is repeated by the same group, then the university policies of scholastic integrity and honesty will be strictly enforced. That means I will report you to the appropriate authorities for more disciplinary actions. So in every assignment, in every exam, you will see this blue box which simply says, I pledge that I have neither given nor received any unauthorized assistance on this assignment, exercise, or examination. You're supposed to sign and write your name and sign it, and that's a part of the pledge that you have not cheated in any way. So the course syllabus, it's divided into 3 subsections. The first section would be just introduction to MATLAB. We will spend probably 2 or 3 weeks because no one has seen MATLAB yet, and that's a tool that we are going to use. So building the proficiency in MATLAB will be the key. The next subsection will be extending what you have learned in 2171 on mathematical modeling. So we will build a variety of different models using the principles we have learned in 2171 to build models of very different category, like lumped and distributed models, and we will see what they are as we go down in the lectures in future. And then we will learn during that phase how to solve each one of these types of problems in MATLAB or COMSOL using appropriate computational tool. So by the time you would have achieved sufficient proficiency in MATLAB to be able to develop the skill of solving engineering problems, both formulating and solving the engineering problems in MATLAB by the second phase. Then the third phase is to answer the question, how does MATLAB solve these problems? So understanding the numerical algorithms that go into these software. Okay, and that will be a significant portion of this course. So there are three segments: MATLAB, model building and solution, and how does the MATLAB solve these problems. So we will be learning about these tools. As I said, there is one recommended required textbook, but there are a number of other recommended textbooks. Those that are keen can check out these books and learn more. As we go along, I will point out and help you individually if you come to me on what sections to read for what time. So that's the material in the course outline very quickly, and that tells you a little bit about the structure of the course and the goals in the course. Okay. If there are any questions, Jillian can pause and take them and answer them at this stage. If not, he can continue to play the recording. Okay, so the first lecture is basically an introduction to get an idea of what computing is, how do computers represent numbers, and if time permits, we will open up actually MATLAB and see what MATLAB is to get a feel for how MATLAB program is organized. Okay, so a brief history of evolution of computers. Computing is essentially doing arithmetic calculations between numbers, addition of two numbers, multiplication of two numbers, etc. And we have found the need for this for over 2,000 years ago. I don't know if anyone can recognize what this is. This is an abacus used for over 2,000 years to do arithmetic operations, additions, multiplications, etc. A more recent tool to aid in arithmetic operation is called the slide rule. Again, we don't use these days, but when I was a student, I learned engineering problem solving with slide rule because MATLAB didn't exist at the time. That shows how old I am. And there is another recording where I go through the principles on which slide rule is designed. I'm not going to go through them today. If you want, you can listen to the past lectures. But it is essentially a device for doing multiplications between any two complicated numbers, long numbers. I'm not sure whether you recognize the third picture here. This is the electronic discrete variable automatic computer called ENIAC. And it's a room full of computers built with diodes consuming a lot of energy and doing very little calculations. And this sets the stage for us to appreciate how far we have come since 1950 to 2018, where the cell phone that you hold in your hand can do literally millions and millions times of calculations compared to this, and is a million times smaller than this room full of computers. Some of the statistics on this is it can do a multiplication in 2,900 microseconds. At that time, it was a huge achievement, and that turns out to about 500 flops. A flop is a floating point operation. So essentially, the time it takes for one multiplication or division. So it can do 500 multiplications or divisions in 1 second. No human can do that. So in that sense, it was already far superior in arithmetic operations compared to the humans. But current day computers can do 36 gigaflops. Okay, not even mega, a giga. Mega is 10 to the 6, a giga is 10 to the 9. So 10 to the 9, a billion calculations. In fact, it's gone even beyond that. Sorry, this one is about flops per watt of energy consumed. Okay, so that's a measure that people use. So it consumes enormous amount of energy and does very little calculations, whereas today computers will produce enormous amount of calculations with just a battery, for example. Energy consumption is very low, 2 watts, 3 watts, etc. Now, this is a room full of computers. It's called a supercomputer in the Department of Energy lab. It's called Blue Gene. And this one has about 1.5 million cores. These are individual process units that are stringed together in this configuration, and they can do 16 petaflops. A petaflop is 10 to the 15. We're talking about gigaflops, that is the range for your handheld cell phones, and this one is 10 to the 15, from 10 to the 9 to 10 to the 15. And there is a race in the world to see who produces the fastest supercomputer. US has been leading that for a number of years, but in the last 4 years, previous 4 years, China led the fastest supercomputer, but this year I think US took over. But still, there is a list maintained of the top 500 supercomputers in the world, the fastest supercomputers, and 250 of them are in China at the moment. This is your well-known desktop to you, which can do about 60 to 70 gigaflops. This is the kind of machine that you will find in the computing labs around LSU. The internals of these are basically electronic components, something called a motherboard that houses the central processing unit. This is the CPU. And when you're talking about cores, this CPU can consist of 4 cores, 8 cores, 16 cores, etc. So each core can do an assigned individual task. So at the same time, a 16-core machine can take 16 instructions and work on them. And this is embedded in this motherboard, and the motherboard has other slots for putting memory chips, as well as external boards that connects to the keyboard and the monitor, and even some data acquisition systems. You can connect this to a thermocouple or a pressure transducer, etc., to gather data into the motherboard. So this is the central processing unit, and these are the memory chips. If you have ever opened a computer, some of you may actually have built computers by yourself, because these are just assembling parts that you can order. Fairly easy task to do, and that saves you some money. You can build a cheaper computer than buying it from Best Buy. Now, this is called a hard drive, and this is essentially a magnetic device that stores enormous amount of information. And we will see how these information are stored. And then the next evolution is the tablet, the laptop, and the way that we interact with these computers is being also evolving. Okay, initially through punched cards and magnetic tapes, then through keyboards and mouse, and then through touch screens. And now I'm sure many of you have used Siri or Google Assistant or Amazon Echo. So we can interact with computers through natural language. But in this course, we are not going that far, because we still need to learn to program using one programming language, MATLAB. But typically a computer, we have seen the contents in terms of the hardware of how we put a computer together, the motherboard, and then all the peripheral memories and hard disks, etc. So the hardware sits in a box or somewhere in the cloud. And to get the maximum out of the hardware, we design something called a software. And the software is broken into 2 parts. One is called the operating system, which is kind of common. And then you have user programs that are very specialized for individual applications. A chemical engineer might find HYSYS and Aspen. A mechanical engineer might find ANSYS Mechanical. So these are user programs to solve specific engineering problems. But they run on the so-called operating system. And the operating system manages all the input, output, the files, their communication between the user program and the hardware. And there are typically few types of software environments. Windows is probably the one that you're most familiar with that we'll be using in this course, but there is also the Linux and the Unix and Android and Mac OS, etc. So those are examples of operating systems. In terms of the hardware, again, there are variabilities. So there are Intel-based machines, the central processing units, and the AMD-based machines, ARM-based machines, and there will be more to come as the design of the hardware gets even more sophisticated and more powerful. At the user level, we have examples like Excel, MATLAB, HYSYS, Word, and these can be run on any operating system. So you will find a MATLAB version for Mac, or a MATLAB version for Unix, or a MATLAB version for Windows. But the MATLAB will look essentially the same in all these different operating system environment, which can run on different hardware, but to the user, it will look the same. So this course, we are going to focus only on the user level skills. So developing the MATLAB skills, the HYSYS COMSOL skills to solve engineering problems. So we also learn how to pose these problems and how answer how the computers solve these problems. Okay, so there are a number of internet resources for this course. Wolfram Alpha is one. The YouTube lectures by me, and MathWorks itself. You can download a lot of MATLAB software from that. academicearth.org, and of course you have Tutera and Coursera. There are a number of these newer emerging online teaching learning material. Wolfram Alpha is particularly a good one for doing a lot of mathematical and symbolic processing, and at this appropriate stage I will introduce. If you have used MATLAB, Mathematica at any stage, it was developed by Wolfram, and Wolfram has a cloud-based service that allows you to do a lot of these mathematical operations. Okay, so are there any questions? If there are, we can stop, and Jillian can take and answer them by pausing this at this stage. If not, we will continue. Okay. So what we are going to do the rest of the lecture today, I will record only about an hour of lecture, even though the lecture time is 1 hour and 20 minutes, because I think we will cover the same material when I'm doing it live, because there are interruptions, interactions, and I'm giving that opportunity for pausing and answering any questions that you may have by Jillian. Okay, so bits and bytes. What are bits and bytes? How do computers represent numbers? So we want to get an appreciation for that. So let's start. In learning, what you do is you start with something that is familiar to you and then build on that to explore newer concepts or generalization of those concepts. And of course, you can ask the question, how did we learn the very basic? As a child, we learn how to count. And so you are already familiar with the decimal-based number system. So if I take a number like 7,354, and I ask you, what does it mean? Okay, each one will give a different answer. Okay, if you are counting beans, this may represent the number of beans. It's or just a number, an integer number, but it can be represented. The 7 here means that it is in the 1000th position, and there are 7 of them. Okay, and the 3 here means it is in the 100th position, and there are 3 of them, and so it is 300. So this is 7,000. 7 times 10 to the 3 is 7,000. 3 times 10 to the 2 is 300. Similarly, 5 times 10 to the 1 is 50, and 4 times 10 to the 0. 10 to the 0 is 1, so it's just 4. So it's essentially sum of these numbers. Okay, that's one way of representing or explaining what this number means. Why is this particular representation useful? Because we see a common pattern, and that is it uses something called a base 10, a base 10 representation. So you have 10 to the 0, 10 to the 1, 10 to the 2, 10 to the 3. It can continue on, 10 to the 4, 10 to the 5, etc. to represent even larger numbers. And you just find out how many of them are in that base position and multiply by that and add all of them to give you the final number. Okay. Why did we develop base 10 is probably a more philosophical question, because we have 10 fingers, we know how to count with them. Now, if I have a decimal number like 7345.523, we extend the notion in the same way, but it is the base is expanded to include 10 to the minus 1, 10 to the minus 2, 10 to the minus 3, etc. So all the numbers, the decimal numbers, are represented using base 10, which immediately means that you need 10 different symbols to represent each unique one at the base. And these are 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so there are 10 symbols that we use, and these symbols could be in Arabic, in other languages, they can be different symbols. But in any base 10 representation, you need 10 symbols, and using these symbols, you can construct any arbitrarily large number. Okay, the question then is, can we represent the numbers in other bases other than 10? And why is it important? Particularly for computers, a base 2 system is important. It's called the binary system. Okay, and there are other systems called octal and hexadecimal, etc., that we will learn to generalize. But why binary system? Because computers basically deal with two states. Okay, they are based on transistors. So the transistors are semiconductors, meaning either they have a conducting or non-conducting state. And similarly, magnets have north pole or south pole. And so we're constructing the machine at the very fundamental level, at the hardware level, using two states. So we need to be able to represent all these numbers in the decimal system in a binary system, so that we can push these numbers through the central processing unit, and a bit pattern means something to the central processing unit and carries out that instruction. Okay, so on, off, north, south, positive, negative, these are all the two system states. So the same number above, 7354, in the binary system will be represented by this number 111001001100001. Now, how did we come up with that? That's called the bit pattern. Bits are just zeros and ones. Okay, and there are only two symbols you need in a binary system, as opposed to 10 symbols in a decimal system. And the two symbols that we have chosen are 0, 1. It could have been A or B or anything else, but by convention we chose 0 and 1 to be these two states. And so essentially what this means is, you, just like we did in the decimal system, find the position and find the base and multiply by it. Okay, so it's going to be how many digits are there, how many positions in the bit pattern? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Okay, so there are 13 positions, and you will start with 2 to the power 0. Okay, and the bases will be 2 to the power 0, 2 to the power 1, 2 to the power 2, etc. as you move left. So there is a 1 there. That means it is going to be multiplied by either 1 or 0. Just like in the previous case, it was multiplied by whatever the base number was, 7 or 3 or whatever. Here there are only two states, zeros and 1 or 1s. So it is 1 times 2 to the 0, because it is in the first position, 2 to the 0. And the next one is going to be 0 times 2 to the 1. So it doesn't contribute anything. Similarly, 0 times 10 to the 2, 0 times 10 to the 3, and then I have 1. So it is 1 times 10 to the 2 to the 4. Okay, and so I'm writing only the non-zero terms here. So t to the 0, 2 to the 0, plus 2 to the 4, 1 times 2 to the 4. And then in the fifth position, I have a 1, so it will be 1 times 2 to the 5. And then sixth one doesn't have anything, seventh one has, so it is 2 to the 7. And then the next one that is non-zero is 10th, so it is 2 to the 10, 2 to the 11, 2 to the 12. I hope you understand it, and if not, you can replay this and think about it. Ultimately, learning occurs in your mind when you say, oh, I understand this concept. Okay, I can repeat this many, many times, but you need to think about it in your mind until it says, okay, this is what he's doing or telling. Okay, so the rule is essentially use 2 as the basis, 2 to the power 0, 1, 2, 3, 4, 5, 6, etc. And you can have as many bits as you need to represent the number. That is a decimal number. So what we are learning in this process is, how do I represent a decimal number of 7345 in a binary bit pattern that you see here. Now, if you carry out this multiplication, 2 to the 12 plus 2 to the 11 plus 2 to the 10, you will find that you get this number. Okay, in MATLAB, there are a number of functions that are available for doing these conversions from one basis to another, from decimal to binary, or binary to decimal, or hexadecimal to decimal, etc. Okay, and we will see these functions later on, but what I want you to focus on right now is understanding the concept of a basis, and a decimal basis and a binary basis. Okay, and in a binary basis, we basically use 2 to the power an integer number, 0, 1, 2, 3, etc. Okay, so you should be able to answer this question. For example, what is the maximum number that you can represent with 8 bits? All the 8 bits are turned. Remember, a bit can have only 2 positions, 0 or 1. Okay, in this case, we say that all the bits are turned on. They are all contributing. So you'll have 2 to the 0 plus 2 to the 1 plus 2 to the 2 plus 2 to the 3 plus 2 to the 4, adding all the way to 2 to the 7. Remember, you're starting at 2 to the 0. So 8 bits will end with 2 to the 7, and then you add them up. Okay, and that's what you see here, 2 to the 0 plus 2 to the 1 plus 2 to the 2, etc. And that is 255. So this puts an enormous limit. If you are using only 8 bits to represent numbers, the largest number that I can represent on such a machine is only 255. Okay, and in fact, some of the earlier computers did use only 8 bits. And then it went to 16 and 32 and 64. Today, most central processing units use 64 bits. And you can see in 64 bits, you can represent really huge numbers because you will have 2 to the power 64. Okay. So here is a table that maps the relationship between the binary numbers and the decimal numbers. So decimal number 0 is binary 0, decimal 1 is binary 1, decimal 2 is binary 1, 0, because this is 2 to the power 0 in the 0 position, and 2 to the power 1, which will be 2. Then we have 3, or what we do is we turn both bit positions and add them up, like 2 to the 1 and 2 to the 0. 2 to the 1 is 2, 2 to the 0 is 1, so 2 plus 1 is 3. When you have 4, you need to add an extra bit to be able to represent 4. So the bit pattern for 4 will be 1, 0, 0. The bit pattern for 5 will be 1, 0, 1. Bit pattern for 6 will be 1, 1, 0. If you go through this table, you will understand how you can mentally map a binary system to a decimal system, or a decimal system to a binary system. Okay, so that's about number representation, at least basic introduction to number representation in computers. And something about if you develop a feel for what a bit is, or what a byte is. You would have come across this in terms of the speed, for example, of internet transmission. I have 10 megabytes per second, or 1 gigabit per second, etc. That's what they mean, how many bits they can transfer in 1 second through the pipeline or the wires or wirelessly. Okay. Addition in the binary world becomes fairly simple. So if I have two numbers 0, 1, 0 and 1, 1, 1, you can find obviously the decimal representation of this and do the addition in the decimal space. But in the binary space, all the computer has to do is takes these two and then just adds them up, 0 and 1, so it is 1. Here you have 1 and 1, so you flip it and carry that onward, just like you do in decimal space. So this becomes 0 and you carry the 1. And then you have already 1 there, so you add that, so that gives you 0 and you carry the 1. So this is how the computers or the transistors actually do the floating point operations, additions, subtractions, multiplications, divisions, etc. Now we need to understand what a floating point representation is. What I've shown you so far is what is integer representation of decimal numbers. The floating point representation is one where you have a fraction or a decimal part to the number representation. Okay, so it's called a floating point because you can move the digits and always express it as 10 to the some number p. Okay, any floating point number can be represented in this format: d dot d d d d d d d, or just digits. It can be decimal digits or binary digits, and 10 to the p. Okay, so you basically use one digit to the left of the decimal place. And anything that is appearing to the right of the decimal place is called a mantissa, and p is called the exponent that appears in the 10 to the power p. Okay, So examples would be, for example, if I take 7,634.562, I can move the dots around, and this is why it's called the floating point. The point floats. 7.634562 times 10 to the 3. Okay, I'm just keeping one digit to the left of the point, and I float the point to the left, and I find out what the exponent is. If I have a number like 0.000042567, I can move the point to the right side of 4 and write this as 4.2567 times 10 to the minus 5. So now the problem just becomes representing each one of the mantissa and the exponent in binary form. So in binary representation, it's going to be 1 dot BBBB. This is a binary bit pattern times 2 to the BBBB, because we're not dealing with the decimals base, we are dealing with a binary base. So our job is to find out what these BBs are to represent a particular decimal number. And again, MATLAB has tools for converting these. So we are not really going into answering the question, how does MATLAB do this conversion? We develop some idea of how we would do it mentally. It's easier to do in one way than the other. But what is most important is for you to understand we live and deal with decimal numbers. When you're doing HISES or Aspen temperatures and pressures, we put them in decimal representation. But MATLAB will have to convert that into binary representation before it pushes into the CPU where the operations get carried out. Okay, so I have a few examples of this decimal representation of the floating point numbers. Okay, 50 decimal, for example, if I want to represent 50 in a floating point, you can represent an integer representation. Obviously, you know how to do that. We just saw. MATLAB has both integer representation and floating point representation. That is something that we need to understand and learn. In fact, every computer language, every system will have both integer and floating point representation. So the way that we would do that is divided by the largest base that you can find. For example, in this case, 2 to the 5. 2 to the 5 is 32. The next one, 2 to the 6, will be 64. That will be bigger than 50, right? Because we want to keep 1 on the left base, right? So we divide and multiply this number, and what you are left with, 50 by 32, is 1.5625 times 2 to the 5. So we have found what is the exponent in this case, and we represent the exponent in binary, which is 10145, and we represent this 0.5625 in binary, which is 0.1001. Okay, so this would be the binary representation of the number 50 in the floating point representation. Okay, in integer representation, it will have a different bit pattern, but in floating point representation, it will have a different pattern. Here, I have given you what it looks like in integer representation, 110010. So you need to identify the type of the variable you're going to use. Is it integer or is it floating point? Then you store a particular bit pattern, the computer can recognize what that number stands for. Okay. So maybe again, time to pause and ask if there are any questions that Jillian can answer. If there are questions that arise after the lecture or during your study period, you can use the Academy to post your questions, and the other students may answer it, or I will certainly answer it. So the learning continues beyond the lecture room in a continuous fashion. Okay, so I have a few other examples of floating point representations that I would like you to study and understand. Okay, so the next important concept for you to understand is the 32-bit and 64-bit floating point representation. It's called a single precision. A single precision essentially means I'm going to use a maximum of 32 bits, and this is called a byte. Okay, 32 bits to represent a floating point number. And of the 32 bits, I'm going to distribute them in the following fashion. So 23 bits in the last positions, these can be just zeros and ones, will represent the fractional part, the part that lies to the right hand side of the point. And there are 8 bits that are used for the exponent. This design is arbitrary. It was developed in consultation with IEEE. I think there's a standard for this representation. And that by design sets the limit on what is the largest number and smallest number that I can represent, because with 8 by 8 bits I can only represent a certain number, 255 we saw, for example, right? So the exponents can range only over that range, but if the exponent is 200 or so, we are really representing a very large number, and that would be adequate for most engineering calculations. But you should remember, by all this, any computer will have a finite capability to address numbers. It cannot, concept of infinity remains a concept. You cannot represent a number that is as large as what infinity is. And we need to learn what are the maximum ranges for integers. Integer using 4 bits, 8 bits, 16 bits, 32 bits. And there are functions in MATLAB available for each one of them. And there is one bit that is set for sign, because you can have negative numbers or positive numbers. So it's a binary state. So 0 is negative, 1 is positive, etc. Okay, so this is the bit pattern for a 32-bit, and this is the bit pattern that will be for this particular number. But you should be able to figure out what the bit pattern is for any number that is given to us. In the same way, there is something called double precision in most computer languages, and MATLAB by default uses double precision always. That means it assigns 64 bits to represent a particular number, and that gives you typically about 16 digits accuracy after the decimal point, whereas the single precision will give you about 7 digits accuracy. Okay, and you're using 11 bits for the exponent. That allows you to express a larger range of numbers. The dynamical range for numbers can be larger, and you still have 1 bit for the sign, but 52 bits for the mantissa part of it. So you can carry 16 significant digits of information. Okay, and this figure essentially shows what are the minimum and maximum ranges from negative 1.8 10 to the 308 to positive 1.8 308. And there are functions called real min and real max that will give you these numbers in MATLAB. Okay, how are we doing for time? So 45 minutes. I'll record another 15 minutes, and then I will stop this recording and post it as lecture 1, and then we'll continue the next class on Wednesday. So the next representation that we would like to learn, basically to see how these can be generalized to other bases, is octal and hexadecimal. Okay, octal system uses 8 different symbols. So these symbols are again chosen from what we are familiar with: 0, 1, 2, 3, 4, 5, 6, 7. So the numbers can use only these symbols. If an octal system uses 9, you immediately know it's not possible. That system is wrong. Okay, in hexadecimal, it means we are using 16 different symbols. It's a base 16. Octal is a base 8. Binary is a base 2, and decimal is a base 10, etc. Right? So in a hexadecimal system, we need to find other symbols, because we have used from 0 to 9 gives us 10 symbols, but I need 11, 12, 13, 14, 15, 16. Again, an arbitrary decision that says we will use the first 6 letters in the English alphabet. So you'll use A, B, C, D, E, F. Okay, and an example will help you understand what that is. And most of you have seen hexadecimal, because the cell phones, the modems, the IP addresses, they are all expressed in hexadecimal. So you will have 6F, 4C, etc. as a number representation in hexadecimal. So in a decimal, for example, if I have a number 675, I know how to represent that. It is 6 times 10 to the 2, 7 times 10 to the 1, 5 times 10 to the 0. In binary, I similarly know what the bit pattern looks like. In octal, how does it look? Okay, in octal, it looks like 1, 2, 4, 3. Now, if somebody gives you this number, and just this number, you have no clue whether it is a decimal system or an octal system or a hexadecimal system, because all these symbols are allowed in all these 3 systems. So somebody has to tag it and tell you 1, 2, 4, 3 in octal system. What does it mean? Okay, once they tell you that it is an octal system, then you just take 1, and this is in the 4th position, a to the power 3. You always start a to the power 0. Okay, so 3 times a to the power 0. Remember, it's an octal system, so 8 is the base. and 4 times a to the 1, and 2 times a to the 2, and the 1, 2, 4, and 3 come from this number. And the position, the base position, tells you what its multiplication for the base is. And when you do this, you will find that when you add them all up, you will get 675. 8 to the power 3 is 512, 8 to the power 2 is 64, 8 to the power 1 is 8, etc. And you'll get 675. So 675 is, I have to tell you, it's a decimal representation. Okay, 1243 is an octal representation of the same number. They are equivalent in representations in two different systems. It's like expressing the same concept in two different languages, right? The basis is different, but the concept that we are trying to convey is the same. So similarly, in a hexadecimal system, I will say the number is 2A3. Notice the A, okay? So the hexadecimal system uses 16 different symbols, 0 to 9, and A, B, C, D, E, F. So I'm saying that 2A3 is the same number as 675 in decimal. How does it work out? Okay, 675 is 2 times 16 to the 2. Okay, the 2 here comes from the fact that we have 2 in that position, but the position is 0, 1, and 2, the second position. So it is 16 to the power 2, and it is 16 because it's a hexadecimal system. Okay, the next one is a tricky one. The base position is 16 to the 1. Okay, but what does A represent? A actually represents 10, because you have 0 to 9, and then A is 10, B is 11, C is 12, etc., all the way up to F. Okay, so you will replace that when calculating this number out. So A actually stands for 10, B stands for 11, C stands for 12, etc. And in the next position, you have 3, 16 to the power 0, and then carry out the multiplication, you'll get 675. So the decimal number 675 has an octal representation, which is 1243, and the hexadecimal representation, which is 2A3. But ultimately, in the computer, it is represented in binary form. So if 675 is represented, it will always need this many bit positions to represent it. Okay, but we can also convert it into other representations for various purposes, but the most important one is the binary one, because that's where all the operations take place in the binary world. And here is a link. This is what I mean by additional learning material sources. This is a link to the ASCII table, and if you click on it, it will take you to a website with something called ASCII. ASCII is American Standards for Communication Information Interchange, or something like this. And there is a table, and the table essentially tells you how we represent various letters and numbers and symbols that are on the keyboard in terms of this binary mapping. Because when I press a key K in the keyboard, what happens? It transmits a bit pattern to the I/O device of the operating system, which takes it and puts it to the central processing unit, and the central processing unit recognizes it as a K or a particular bit pattern. So there is this ASCII table with, I think, printable. There are a lot of non-printable characters that are assigned a bit pattern, and they give you all three: the decimal representation, the hexadecimal representation, and the binary representation, the actual character symbol. Okay, so if you go and look at, for example, exclamation mark, in decimal it's the 33rd position in the table, in hexadecimal it's 21, in binary it is 001000001, etc. Okay, so when you press a particular key on a keyboard, this is the bit pattern that is transmitted by the computer, by the keyboard to the computer. So here you have, for example, uppercase A is 65th position, uppercase B is 66th position, etc. So we needed to get organized with all these information communication mechanisms before we can really do anything useful and meaningful with the computers. Like constructing a word processor essentially means I'm constructing words. It consists of these symbols, and there are uppercase and there are lowercase symbols. We need to make a distinction between them. And so development of these standards was a key in achieving significant advance in computer evolution. So this is using 7-bit patterns, and so you can represent up to 128 different symbols. And when the other languages needed to be represented, this was extended to 256. By adding just one more byte, eight bits, you can represent additional 128 different symbols. These are the symbols with accents and the Cyrillic symbols, etc., that you will see. Okay, so that's what an ASCII table is. Let's go back to the lecture notes, and maybe this is the time I should just start opening up the MATLAB and show you how we can explore some of the concepts that we discussed right now. So when you go to any lab, or after you have installed MATLAB on your own computer, you go to the start and then search for MATLAB. Okay, so I hope I'm recording this from overseas, and I hope I will be able to access the license in Alberta, and it will start. This I will do in the class. Often I will demonstrate live, so I will switch between the lecture notes and to the program so that you actually learn how to start and how to play with MATLAB. Okay, so this is the flash screen for the MATLAB, and it will check out the license from LSU license server. If you have your own local installation, you can use it by starting the local version, license version. Otherwise, if you're connecting to a campus from home, you need to have something called a VPN, and I will show you more about it in one of the labs. I guess it is taking time to check out the license, but I hope my VPN is connected. I'm doing this at 4 a.m. As you can see, I'm in Ottawa, and so the license connection, the license server may be down, or the network is obviously up, and I'm connected to LSU campus system authenticated, but the server doesn't seem to be, yeah, there it is, because of the delay, I guess, from the distance. So when you start MATLAB, this is what you get. Okay, the way that you interact with MATLAB would be through something called a command window. Okay, and it has several other windows. You can customize it, reorganize it, but this is a standard default configuration. And it is still trying to initialize something. It tells you what the status is. Once it is ready, it will give you a prompt like this with two right-angled carets and a cursor that is blinking. And you will be able to enter commands to MATLAB, and the MATLAB will interpret the command, execute the command, and give you the result. It's called an interactive or interpretive environment, which means every command that you enter is acted upon instantly and the response produced for you. Okay. There are a number of other windows that you should know about. Of course, you are familiar with the typical ribbons and icons and menus on the top that is typical for Windows and most other operating systems. But on the left-hand side, you have a current folder. Okay, as you know, in the Explorer, files are organized in the form of folders, right? So here you have a folder called Docs. Inside that, I have a folder called Courses. Inside that, I have a folder called F18ChE2176. Okay, so this is called the path, and if you enter any command, there is a sequence of search procedures that it will go through to interpret what you are trying to enter and act on it. So this path should typically be set to your current path where you're doing your homework or assignment. For me, it is going to be the path for I guess the path doesn't exist. Let me go to. Okay, so this is for this course, the folder, and within this I have for week by week lectures, and then the lecture by lecture. Okay, so this is the folder. I don't have any functions in there to show you, but what you need to know is that a path is important. Okay, so you control the path by either typing the path here or by selecting from this current folder. Can go up the folder, you can open up new folders, and when you take the cursor near one of these icons, it tells you what it does. Okay, For example, this one goes back by 1, this one goes forward by 1, and this one goes up the tree by 1, etc. The next important window is the workspace window. The concept of a workspace is very important for you to understand. When you are dealing with MATLAB, whatever you enter, create a variable, it stores a copy of it in the workspace. It's like your desktop. It will be cluttered. It will have lots of numbers, etc. as you create them. For example, in this command window, I say a is equal to 5 and enter. So what I've done is I've created a variable called a and assigned it a value of 5. And immediately it shows in the workspace I have a variable called a. Its class is called double. Okay, this is why we talked about single precision, double precision. So this is a 64-bit representation of the number 5, and its value is 5. Now I could come and say a is not 5, it is 1, 2, 5. Okay, so what you see here is I put square brackets and I put 3 numbers separated by distance, and this is called an array. Okay, and it replaces the old a with an array which is of the size 1 by 3. That is 1 row and 3 columns. Okay, and the numbers are 1, 2, and 5. So you can create really very powerful arrays and variables. And I can create another variable, lowercase is 6, for example. So the lowercase a is different from uppercase a. So you have to be aware that the variable names are case sensitive. Okay, and I can define another variable called b is equal to 7. So in my workspace, I have 3 variables now. And if I want to do an arithmetic between them, I can say a times b. I'm saying multiply a and b, take the numbers, the values from the workspace, and return the answer. It's 42. How did it do it? It took the binary representation of what is stored in a, which is 6, and what is stored in b, which is 7, and pushed it to the CPU with this operator. This is called an operator. And that tells the CPU that I want these 2 bit patterns to be multiplied. And it produces a new bit pattern. And the new bit pattern is sent back through an I/O unit to represent it in decimal space on your screen as 42. Okay, everything is digital, everything is binary pattern. So when you press a key, there is a bit pattern that is determined by the ASCII table, right? And similarly, when I enter this operation, the bit patterns are constructed and sent to the central processing unit, and the operation is done and the answer comes back. And when the answer comes back as 42, how is that represented on the screen? The screen is also a set of bits. There are about 2000 by 1600 bits in the horizontal and vertical direction. Each bit is a light, a dot. It's called a pixel. And the pixel can be turned on or off. Okay, when it is on, let's say it's white. When it is off, it's black. So to construct this 42, it needs to know which bit patterns to turn on and which bit patterns to turn off in that particular position. So this can be maybe 9 by 6 or 9 by 7. That depends on the screen resolution. Okay, but the point that I want you to drive is that even screen representation, keyboard representation, everything is done in binary format. So we need to understand and keep aware of what this binary system is. That's the reason for introducing you to that. Okay, so maybe that is the, I'll show you the base conversions. Okay, so suppose I'm given 42 and I want to find the binary representation of 42. Okay, how do I do that? Now this 42 is saved in a variable called ans. Ans is a variable that it automatically created because I didn't give a position to store. For example, if I had done c is equal to a times b, then a times b will be stored in a new variable called c, and c will appear in here. Then I can address that by simply calling a c. If I just type c, it prints out the number. Okay, so now I'm interested in finding, you don't have to use c, then the variable ans will be used, but the next time you carry out a similar operation, ans will be replaced with the result from that operation. So it's always a better idea to carry out an operation on the right hand side of an equal sign and assign it to a variable, a new variable that you haven't used, so that it doesn't overwrite it. Okay, so how do I convert this decimal to binary representation? These are called functions. MATLAB has tens of thousands of functions. Each function does a particular job, and we need to identify what the job is. Right now, the job is to convert 42 into binary bit pattern. Okay, so we need to search for it. So here is the FX icon, and essentially allows you to browse for functions. This is how you begin to learn about the tens of thousands of functions that are available. So you just click on that, and it will tell you what are the functions available, and you can search for it. So I can say bin, and it will tell you all the functions that are available in binary format, like bin2dec. You can guess it's going to be binary to decimal conversion. Then you say, oh, maybe I don't want that. I want the decimal to binary conversion. So you type that. So immediately it tells you all the functions that start with the symbol DEC, but here is one that says DEC to bin. Okay, and when you take the cursor to that, it gives you additional information. Okay, DEC to bin, and you put D as a decimal number, right? So you can click on that. It will open up the function for you, and you can just complete that. So I want C, okay, decimal to binary of the variable that is stored in C, and its bit pattern is 101010. You can verify because you know what these bit patterns represent. So there are a whole series of such conversion functions to convert from one base to another base. Okay, so maybe that's the right place to stop for today. If you have other questions, you can ask Jillian at this time, or as I said, you can post your questions through Acadly chat box or messaging box, and we'll try to continue to engage through this. And I'm stopping this at 1 hour because this is the level of material I will typically cover in 1 hour 20 minutes with Q&A and discussions and responding to students' questions. So we will be keeping in pace. We will not be falling back. And I hope through these pauses that you have had today, you have reached the end of the course and you've been able to reach till this end. If not, if the time has arrived for you to leave, then watch this recording afterwards. Okay, and I will instruct Jillian to stop at 11:50 and let you go. Once again, with my apologies for not being present there. I hope you find this lecture a useful one to get introduction to the number system. I will see you again virtually on Wednesday because I am at the workshop the whole week, and then the next week on Monday I will be in person in the class. So I will record the next one and upload it soon.